Okay, well, does someone want to get us started with a question? You can unmute yourself or raise your hand and I will unmute you, or you could just write it in the chat for a first thing that you guys want to go over. And I can share my screen so you can... Has it been okay, like, following the lecture videos? I kind of, like, forces me to, like, see how long they are, too. I sort of miscalculated, like, one was a lot longer than the other. But... problems with the Claisen reaction. Okay. Let's look at... I need to... see. This is... okay, did I actually have any Claisen questions? Oh, these are Claisen. Okay, wait, now I've lost my group chat though. I want to see my group chat. Can somebody type something in the group chat again so it pops up? I think it will pop up. Oh, wait, more chat. Aha, thank you. Okay, so I will put this group chat over here in the box. Okay, so these are from Claisen. Let's see, let me put this box. I'm gonna make this box smaller. Oh, sorry guys. I made... okay, so in a Claisen, it's like an aldol, it's just that the nucleophile and electrophile are esters. So in a way, for the nucleophile, it helps because there's no thermodynamic or kinetic enolate possible, right? One side is the OR group, and so that cannot be where you make your carboanion. So it has to be on the other side of the carbonyl. But when you then attack, let's see, when you attack your other ester, right, then that ester knocks off its leaving group, right? So here, yeah, you only have one nucleophile possible, and then when you attack the ester, then instead of acyl addition, you get substitution, where your OR group gets kicked off as the leaving group. And that means that you form two ketones instead of having one ketone be turned into an alcohol. So when you're looking at the retro of one of these, the main thing is that the ester group that still is an ester, that hasn't lost its OR group, that ester group was the nucleophile, had to be the nucleophile. And for it to work, it also has to have two alpha hydrogens. So if you're seeing, I mean, I don't think anyone would trick you this way, but like if you see like a product where when you take this off, the nucleophile doesn't have those two alpha hydrogens, then something's wrong, right? So that basically means like you cannot be very hard to have like two R groups here. So we can look at these. So this is sort of, these are cross. So some of these are aldol and Claisen. The trick is to sort of find, you go between the two ketones, and then you can cleave basically on either side, right? Now, if this is, if this was actually a Claisen, let's see if I can, I'll draw over here. Oops. So in sort of like a retro Claisen, right, this has to be the nucleophile, sorry, with this, right, and this would have to be your electrophile. So breaking these up, right, so you have to basically, in this sense, you can't break here if they're two esters, okay? So breaking here implies that one is a ketone. If you want it to be a true Claisen, then you have to break here and keep your nucleophile ester intact. So that would make this your nucleophile, and then your electrophile is also the ester, right? But that OR group is now gone. It was the leaving group. Okay, do you want to, do you have like maybe a specific chapter or specific problem that I could, or any other, I don't know, was that clear enough? You guys can like unmute yourself too, if it's easier to explain. Okay, a retroclaisen, so a retroanalysis is when we're looking at a molecule, we have the product, and they're asking us to find the reagents, like how would we make this? So straight synthesis is just going from reagent to product. A retroanalysis is going from the product backwards to the reagents. Chapter 22, page 39B. Is it? Okay. It's not one of these. No. Okay. Chapter 22, 39B. Asking. Sorry, I gotta look up the book. So,
I'm sorry. I meant it's in the slides.
Oh. Where in the slides?
Just if you keep scrolling down.
Oh, my slide, page 39.
Yeah.
Ah, okay. 30. Okay, so these are conjugate addition questions, basically. Yeah, so we're in the Michael reaction portion. So the key to also with these is kind of at first, right, is right away is identify who's going to be a better nucleophile and who's going to be the better electrophile. They usually kind of make this super obvious by having a structure right here where these hydrogens are super acidic. So this is going to be the best nucleophile. And then they're offering you this conjugate ketone as your electrophile. So this one didn't really ask you for mechanisms, right? But basically, one of these protons gets deprotonated, turns into a nucleophile, an enolate, and then because these are Michael reactions, as we said, enolates prefer the conjugate addition, right? So they're not going to attack straight at the carbonyl, right? They're going to preferably attack, like I have it here, at this secondary position, and so that's why you have addition here instead of at the carbonyl. And because of that, so this double bond, the negative charge ends up in between and is also stabilized by the ketone. but then it gets quenched, so your ketone actually stays in place. Yeah. Is there anything else about this one? Yes. Yeah. So let's look at. Ooh, wait, where in the slides is that section? Sorry, there. So I have a reminder slide where I show the pKs. Do I? Where is it? Oh, it's probably under a box somewhere. No. Oh, here it is. Okay, sorry. Okay, yeah. So here, right when in the first chapter when we learned about enolates, enolates are formed by a base basically deprotonating, or there's the acidic way too. Sorry, but basically you have to deprotonate this this proton, and so basically between two ketones, this is the most ready enolate, right? Because as soon as you form that negative charge here, it can do resonance on both sides. Is there carbon missing in part B of that problem? Completely possible. Let's go back. Let's see. So we have our carbonyl that stays. We have this. Ooh, yes, there is. Yes. Good catch. So this is why count your carbons, but for sure, yeah. So this last one is then going to be bonded to the cyano. Like this, yeah. So this is our new CC bond. Yeah, sorry about that. But yeah, so I mean, a lot of these reactions are in equilibrium, and when they're asking you like an intramolecular aldol where there's a aldehyde and a ketone and both can be the nucleophile or the electrophile, because these are reversible, like maybe it will go one way, but it'll typically like eventually find the equilibrium where the more electrophilic acts as the electrophile and the more nucleophilic acts as the nucleophile. So they are fairly selective. Like with this reaction, for instance, you would not expect to like form this enolate here. And like attack over here. That's not the best reactivities for these carbonyl structures, so you wouldn't see that as a major product or even any product at all. Further Robinson annulation, would the product or any of the ever okay, here we are at the Robinson. Would the product of the full Robinson annulation product, would it react with starting material that would maybe still be in, so like another, yeah, let's see, so you're thinking like maybe you've made this product, and now I could form like another enolate here and maybe do more reactions. I would say like yes in theory, but basically by the time you're here, like by the time you're at this point, you've used up all the possible electrophile. It's already been turned into the ring. So maybe you're forming some new enolates, but at the end of the reaction, you would, quench the whole thing with water, and that would be the only product. There's nothing. Now, if you like had more base and added a new electrophile, then like yes, like a raw, like there are places to do more reactions, but that's not. I mean, like you would have to really set it up to do that. So I think you're thinking of this one with the product. Yeah, I mean, so like in this case, right? You have you started with this ester group, and it's still there. So yeah, this ester group is not like it could get yes, like yeah, you could like do reactions at this ester group if you set it up for that. But generally you'd have to like take this product and then put in new conditions. It's so quiet. Slide 22. Okay, going back up. I'm glad I numbered these slides. Okay, so this we were looking at a Claisen condensation. So this is an example of a retro Claisen. So again, you can find like, oops, let me find where you have your ester still, right? And this is your nucleophile. Now you see this carbon, right? That's going to be where my negative charge is, and it includes this group, right? So that's how I get this as my nucleophile group, and this is a straight Claisen, right? So this one it's going to attack itself, right? It's going to attack another molecule of the same ester, right? And so same thing, it'll attack. Oops, attack the carbonyl. Okay, then you'll get like a tetrahedral intermediate, and then you'll have an O- group, and then that will come back down to reform the carbonyl, and your this group will be your leaving group. So that's how, and right, so then like this is here, and this guy is attached here. Does that answer your question, Anna? And I also, so like what, like here is like what base, so you want to make sure that you match your R group. And so you can make this base. Like the more complicated it gets, the more annoying it is to like find the right base, but you can totally get this. So. Okay, Tuesday is chapter 21 and chapter 22, right? Because we did enolates before spring break, and it'll be these slides. I think it's still going to be a 10-question long quiz, though, so it'll be a mix of both. I mean, a lot of the enolate questions sort of play into this chapter too, so like it's basically mixed. So yeah, 21 and 22. Anything else? I could talk about other things too. I think so far still trying to figure out how the final exam will work, but I'm trying to keep everything as similar as before, so it's going to be a multiple choice, but it may or may not be like a ACS, official ACS. Can go over a melanic ester. Okay, yeah, and slide 14. Okay, let's do. Sorry. The average on exam 2 is 77. It was in the video, but I didn't post a full breakout of that. Yeah, I mean the average was a little bit higher than before, but so far we're still sort of following the trends for the syllabus breakdown. That will change depending on how many students take the pass-fail option. I don't know how that will work out, and the deans haven't really outlined yet exactly what the pass and the fail, like what the cutoff should be. I mean, they're still deciding that. So there may be changes to the syllabus breakdown of letter grades based on how many students sort of opt out of it. Okay, so let's just go over 14 and then we'll go over to the end of chapter 21. Yeah, so this is sort of just giving you, this is your bulky base. So it wants to do the kinetic enolate, and this is the unhindered. So it gives you the thermodynamic. So the bulky base, basically like the bulky, like if it's like a big base, it doesn't want to come in here, right? And it's easier for the bulky base to come here and deprotonate that proton. So that's why you get the most, let's say, exposed enolate anion, right? This is easy access for something bulky to get at. But this is not as stable, right, as having the anion over here, right? Here you have you're more substituted, right? So this is a more stable enolate, but you have to have access to this proton over here, and so that's why the choice of base can let you decide when enolate forms preferentially. In both cases, you'll still form a mixture, but you might be like 98% of one and 2% of the other, and that's like great by chemistry standards. So yeah, LDA, and especially I guess I should have maybe said like LDA at -78. Oh, you know what? It is not. There are a lot of other bulky bases, and there's also lots of variants on LDA. So that's lithium diisopropylamine, but there's other amines that are also bulky that you can use. It's the only one that the book introduces you to basically for this. So for the purposes of the test, the LDA is the only one you'll see as being the kinetic. But plenty of other bulky bases exist that will do this. So just to finish this one off, so basically, based on where you form that nucleophile, you'll either get addition at right at this carbon, right? You'll form this bond, or you'll form I flipped it over, right? But yeah, you'll either form here or here, like link here or link there. Okay. Marissa, is that okay for slide 14?
Hi, sorry. Could you just explain how you got, I guess like how off of the uh, product after the thermodynamic enolate, I
Mm-hmm.
was confused how you got all of those, I guess like extra branches, or maybe, I
Okay.
don't know, I
Okay. Yeah, I may have put in too many. Let's just double check. So let's say, so this pink one here is off of, so let's say these are off the nucleophile. So that's this one and this one and this one, right? Because this was where the enolate was before. Okay, and then what are we adding on the electrophile side, right? We're adding a methyl group and then a three carbon chain, right? So this is that methyl group, and that's 1, 2, 3 that are attached off the. So this carbon is here. Yeah. So it does, yeah, it gets a little bit crowded, and that's why there's no, you can't form a double bond, right? Because everybody's got enough carbon arms, right? You can't remove a carbon, so there's no way to make that double bond. Okay, let's look at the end of 21. It was the okay, so how to make yeah, I had somebody ask for a video on this, so I guess we can do it now. Yeah, so beta keto esters are like we've seen, right? These protons are really acidic here, so these are great at making enolates. And in this case, in these reactions, we're not adding another carbonyl as the electrophile. We're still talking alkylation or bromination. But the main thing that's sort of different is that once you form your enolate here, and then you've added your electrophile, you now have this ester group that is like people were asking earlier, right? How maybe that ester group at the end of like a Robinson reaction, or maybe would like continue doing reactions, and that can happen. And so that's an example of this, right? Is where now this ester is in a lot of base, and if you have heat at the end, right? This will just keep reacting basically, and there's ways of trying to stop that, I guess, but it can be tricky, right? So generally, when you see these, like that can keep depending on the conditions, you can keep reacting with the ester and get the decarboxylation. So the first part is the same, right? You deprotonate, form a stable anion here, right? It can do resonance on both sides, so this is a really stable enolate. That's your nucleophile that goes after an electrophile, and in this case we're just doing an alkylation, right? So this is any R group is here, and now you could like quench and hopefully leave it there, but if you keep going, basically if you add a lot more base and you have more heat, then the base does react with your ester, right? This is basic hydrolysis from the last chapter when we did carboxylic acid derivatives. It attacks the carbonyl, you get that tetrahedral intermediate. This comes back down to form the carbonyl, and the ester is your leaving group. These are under basic conditions, right? So you lose, right? So plus is coming off. Right, so then you would quench, under basic conditions, right, you would have your deprotonated carboxylic acid. You can't just have the carboxylic acid at the end because you're in base, right? But once you quench the reaction with a bit of acid, and then you apply heat. So this is sort of a separate step, like to get this to decarboxylate, like you can leave it, it's stable, but if you heat a beta ketone carboxylic acid, it comes off, and that's how you get the decarboxylation. You lose the CO2, and you're just left with your ketone on the other side. Yeah, so you do have to use heat, like you have to purposefully want to decarboxylate, but if you make this sort of structure with the two ketones and the carboxylic acid, then you can go to this decarboxylation step. So this kind of all figured, like this would be good like synthesis, right? If you, right, because basically making this, right, you guys know how to make this a different way now. This is basically a Claisen product, right? So a Claisen product can be treated with more base quenching and heat to decarboxylate one side. So keep that, yeah, that's, all these reactions do kind of go together. Okay. More questions on chapter 21? Would more base have to be added to perform hydrolysis? Okay, good question. So generally with these equilibrium ones, you use like a lot more base, but so okay, yeah, in real life, yes, if you had like an excess of this base, it could affect your reaction. But these are actually these are done stepwise for a reason, right? You use your base to form your enolate, and then that's it. You use up that base and you're done. Then you add your electrophile, right? So this, when you get to this point here, there shouldn't be any more base left. You've used it up. You're done. You work this up. You do a separatory funnel. You get this finished. And then, yes, then you would put this reaction with like some fresh base to get it to go, to then do the hydrolysis. So for the purpose of any like exam questions, we would certainly have that be completely stepwise. Now, does trace base like do side reactions? Yes, of course. But I mean, this is why most syntheses are never 100%, besides like the click reaction. So to answer your question, like, yeah, you would have to add a new equivalence of base to react with this ester. Yeah. Yeah, are we feeling pretty confident about condensation reactions? I hope so. I mean, there's not really too many, there's no new mechanisms, right? Pretty much, besides some of the conjugate or like the aldol dehydration, most of this is all mechanisms that you've seen before, just combined a different way, right? We're still doing acyl addition or acyl substitution. From the end of chapter 21. Yes, like one, a different one, or one of these that was in the. Do you have a specific one in mind? Okay. I tried to put in a lot. Let's see. End of chapter 21. It's a good one. Let's see. Can we go over the synthesis question from 21? This first one, or sorry, is it 1, 2, or 3? Okay, all right, so how to synthesize this one. Okay, so yeah, so part of that is definitely first, start looking at your molecule, and then see what has been added to your carbonyl, right? So you have a carbonyl, and all of these things were basically added alpha to that carbonyl, right? So the alpha position is where you're going to make your enolate. So basically anything that's bonded to that alpha position is a new group. Then, so depending on this R group, that's where you would choose either the acetoacetic acid or the malonic ester, right? So the malonic, basically, it's just this difference here. If you start with the malonic ester, then you're going to end up with an ester on the end, because there's two esters, right? So you get rid of one, but you're left with the other. If you start with acetoacetic ester, you lose one ester. You always have to lose an ester, but then you're left with this acetone group, right? This ketone. So depending on this group here, so if this had been OR, then I would have wanted to start with an OR over here. And if it had been like a ethyl group, then I would have just, started with a different acetoacetic ester. So deciding which one you're going to start off with is the first thing. And then the second thing is these are two different alkyl groups that you're adding, so you have to add them sequentially in different reactions. You can't just make the enolate and then put both in the pot, because then you might get two of the same attacking, two of the same on there, or so you have to do it sequentially. There's no limitation. Like, you can do it in either order. In this case, there's really not an issue. They're both good electrophiles. Like, adding one does not affect the other so much. So then, so you form your enolate here, right, with your base. Remember that you want your base to match your ester. Although in this case, you're going to get rid of it anyway, so it does not matter as much. Then this enolate will attack your electrophile, right, with your alkyl halide. So it'll attack this carbon and displace the bromine. So again, you just count your carbons, right? 1, 2, 3, 1, 2, 3, and then the isopropyl group. And then like this would basically, that would be like the product for your first reaction. You would work this up, and then you would add base to it again to deprotonate that second hydrogen. That enolate would then come attack that carbon and displace that bromine. And so, right, so this carbon is that carbon there. So then you have to remove your ester group, right? If there's no ester group at the end, and so that's when you would then do hydrolysis. So again, new base, new conditions for hydrolysis, and then decarboxylation. Do you have to start with acetic acid or ammonia? Okay. Yes. So could you do it with say like just this, right? Yes, except okay, I guess the issue, also I shouldn't have put in this, that shouldn't have been there. Yeah, okay, so the issue with that is, no, I think you could, but then say you make your first one, right, and you add R, and now you want to add base again, right? So now then you have a choice of enolates, right? And that makes things, I mean, then you have to be careful about that. Whereas, so I guess basically by using the acetic ester, you avoid that there being any mixing of where the enolate forms, right? Because once you have this, like this is the only enolate that's going to form. You don't have to worry about forming enolate here, and then you can use like weaker base. So if you did it with an aldehyde, like a ketone, you would just have to use stronger base, and then you would, you'd have a major depending on the base, like you could do your thermodynamic, like you use NaH to get your thermodynamic enolate, but yeah, you would probably lose a little bit of yield. Yeah, you don't necessarily have to use the you don't have to use this this reaction in particular. It's just if you want to use like the weaker bases, right? These are so acidic that works that way. Like it's a lot easier to add sodium hydroxide than to do like an LDA or like a sodium hydride reaction. But again, that's a little bit more of on the practical side. You guys don't have to know that. Yeah, so I mean, in a test, if I wanted you to do like a malonic ester, I would tell you from this starting material, I guess, or I would tell you like start with either of these two. This is gonna make for really weird YouTube videos. Like, why is she not saying anything? Yeah. For the quiz, it's gonna be similar, like the Blackboard. I think it will be you'll have to answer, like the questions will appear one at a time instead of all on one page. I've heard Blackboard does not do very well if you like cycle between them back and forth really quickly. So try to do them in order, but you can go back if you made a mistake. And I hope no one will have technical difficulties. I'm not sure how to help avoid that, but for sure, if you lose internet connection and like for sure something happened, just like I'll be online, I'll be watching. So like email me right away and be like, I need to get back in, and I can even like look at Blackboard and say like, yeah, no answers were saved. Doing the questions one by one I think will help because it'll save after each one. So hopefully, if like there is a glitch, like I guess you catch it, and you know exactly like where it got cut off. But basically, yeah, tell me immediately, and I'll let you come back in to the quiz. But if you wait till after the answers are done, then obviously I can't say like, oh sure, maybe you had a technical difficulty. One attempt per question. I have to check Blackboard, but yes, I mean it basically, you have one attempt at the quiz, but you can say do question number 1, do question number 2, and then be like, oh no, I think I did something wrong, and then go back to question 1 and fix it, and save again. But then it'll like at the end, like there will only be one submission button, right? Like once you have gone through, you submit, and that's when it really gets sent. Okay, so about the curve changing if people go pass fail, this is like really new to me. I don't know. I don't. So basically, I expect that a certain number of people go pass fail, which is totally fine. It's a great option if you want it. But then, so I obviously I won't just do the curve out of the letter grade people. That would be crazy. But I assume that scores will change depending on whether you choose pass fail. Maybe not. Maybe we'll stay about where we are. I expect the class average to be higher than a C+, considering the circumstances. But basically, right now I'm trying to stay as close to the syllabus. If after people pass fail and then like maybe they drag it down, or I don't know what will happen. So I don't want to promise that nothing will absolutely change. But I definitely will not curve only the people with a letter grade, right? That wouldn't work very well. Okay. Yeah, no, because obviously I assume the people choosing letter grades are going to have good letter grades. I'm not going to make half of them have lower grades. Yeah, and exam 3, I think will be similar to exam 2. It's just exam 2 ended up with like way too many written questions to grade. So there will be some that you scan, but I think maybe it'll be a smaller portion and maybe fewer questions. Can you upload the answers to the questions at the end? You're right. Okay, they're in the video, but I never uploaded them. Yeah, I will make a note. Sure. yeah, so I scheduled another Zoom for right before the quiz, because I assume people might have some new questions. But regardless, the quiz will happen at the scheduled time. So if no one has questions, we'll just take a break and wait for the scheduled time. But the quiz will be at a set time. Do you predict the synthesis? I think I hope that they. I mean, I think there'll be similar difficulty. Probably like the Vidig one that had multiple steps, where it was just like, okay, you have to you want to get to the Vidig, you have to protect one of these alcohols selectively. How do you do that? So that kind of like multi-step synthesis, I think there will definitely be one of those. And a few of the easier written answers. But I think I want to have more synthesis and more critical thinking questions, so that will like fit in more with the open book online environment that we're in. I'm not gonna have you do a bunch of mechanisms, because obviously that's not actually gonna get you to think about these if you just have the notes. For the point worth, I think they might actually end up being worth more points, because there will probably be fewer questions. Okay, well, if that's that, we can stop there, and again, keep using the discussion boards. I think that would help. Would you say the letter midterm grading is a good indicator of where we stand in class? Yes, I think so. If you finish, if your homework shows up in Blackboard. If it doesn't, then you're missing like 15% of what I calculated was a 0, because I didn't go through and copy the grades from Connect for the midterm grade. I will absolutely make sure that I have everybody's homework grades before I calculate the final. But yes, I figure when I calculated the midterm grades, I used I wasn't sure after the online exam if the syllabus rubric would still give me a good breakdown, but it still pretty much applies. So yeah, that's what I calculated based on the 2 exams, the quizzes, and the homework sets that we had already done. Okay, but I push back. So pass fail option. No, the withdraw deadline moved to the 8th of April. When is your pass fail option? The 24th, and the exam is on the 17th. Ooh. Yeah, I think I can do that. Let me just check. I can certainly, so part of the exam 3 will be multiple choice, so I can certainly have that posted at like right sooner. Let's see, 17/24, that's a week. I don't know, Ajetta, I don't want to promise and then not come through on this one. I'm going to say definitely the multiple choice. But yeah, the grading on the PDFs took me like all of spring break, so I don't, and we will still have like a quiz to prepare for, so I'm gonna try. But I don't want to promise. Yeah, so the exam, we're keeping it all multiple choice. I don't want to change things midstream here, so it's going to be multiple choice, and it's going to be proctored, like it's going to be given through Blackboard. So it'll be a Blackboard style question, probably with like randomized order and stuff like that. Yeah, and it'll be timed. Is sort of the only way to. I mean, you know, obviously we're trying to keep everybody honest. I know that that's hard in an online scenario where everybody has group chats, but yeah, we're going to try to keep the multiple choice exam as honest as possible and time it and make it randomized. And so, you know, if you cheat, you'll lose time. That's the best we could do. Maybe could people wonder. Yes, that would be helpful. If you're on the fence about pass fail, let me know and I could certainly, yeah, give you a grade sooner. That's a good point because I assume it won't apply to everybody. So yeah, if you're unsure about your pass fail after exam 3, let me know and I'll put you on the top of the list. Okay. Does that seem good? All right. Well, thanks everybody, and yeah, good luck with the studying, and yeah, use the discussion board, and we'll see each other again right before the quiz on Tuesday. Okay. Bye bye, everybody.